On September 12, 1944, Captain William Curtis crouched inside his burning Sherman tank, watching his loader die because German 88mm guns could punch through American armor at ranges where Shermans couldn't effectively return fire. 29 years old, 8 months commanding armor, 11 confirmed tank kills. 3 times his crew had barely escaped before their tank exploded. The Germans had positioned Panther tanks in the hedgerows with clear fields of fire. Curtis was part of the 3rd Armored Division pushing toward the Siegfried Line. His job was breakthrough operations, smash German defenses, create gaps for infantry exploitation. Simple in theory, catastrophic in practice. The problem wasn't crew training. Curtis's men were veterans. The problem wasn't tactical doctrine. American commanders understood combined arms warfare. The problem was physics. German 88mm guns could penetrate 100mm of armor at 1,000 yards. Sherman frontal armor was only 75mm. The Sherman's 75mm gun could barely scratch German heavy armor at combat ranges. American tankers called Shermans Ronsons. They lit the first time, every time. By September 1944, the 3rd Armored Division had lost 117 Sherman tanks to German anti-tank fire. 117 crews, 585 men killed or wounded. All killed the same way. 88mm round penetrates frontal armor. Ignites ammunition, crew has 8 seconds to escape before the tank explodes. Curtis's gunner that morning was Sergeant James Kowalski. Detroit kid, sharp eyes, steady hands, 14 confirmed kills. They'd worked together for 6 months. Kowalski was tracking a German position through his periscope when the 88mm round hit, penetrated the Sherman's glacis plate at the weld seam. The round didn't detonate immediately. It ricocheted inside the crew compartment for 0.3 seconds, struck Kowalski in the chest, then detonated the ready ammunition. Kowalski died instantly. If you want to see if Curtis's concrete armor actually worked against German 88s, hit that subscribe button and like this video right now. What happens next is absolutely insane. Back to Curtis. Captain William Wild Bill Curtis had commanded tank platoons since North Africa in 1942. He'd seen the evolution of armor warfare from early engagements where Shermans could penetrate Panzer IV armor, to mid-war parity where both sides had comparable capabilities, to late 1944 when American tankers faced an unwinnable physics problem. German heavy tanks, Panthers and Tigers, carried 88mm guns that rendered 75mm Sherman guns obsolete. The armor thickness differential was equally dire. A Sherman's frontal armor could stop small anti-tank guns and machine gun fire. Against an 88mm round, it was tissue paper. The round went through like a hot knife through butter. Curtis had survived 3 years of combat through a combination of tactical brilliance, aggressive positioning, and pure luck. He understood tank warfare at a visceral level. He knew the engagement distances where Shermans could win, close range, surprise attacks, flanking maneuvers where German tanks couldn't bring their superior firepower to bear. He'd mastered the art of using terrain, using speed, using the numerical superiority of American tank formations to overcome German technological advantages. But Curtis also understood the fundamental limitation. If a German heavy tank saw a Sherman first, the Sherman would burn. The losses in September 1944 reflected this reality. Every engagement cost American tanks. Some engagements cost German tanks too, but the attrition favored Germany. American production could replace lost Shermans. But could it replace 585 dead tankers? The mathematics of armor warfare were brutal. A Sherman cost roughly $100,000 to build in 1944, expensive but replaceable. A trained tank crew cost years to develop, irreplaceable. Yet American doctrine prioritized replacing tanks over preserving crews. New Shermans arrived weekly from American factories. Trained crews arrived monthly at best. The imbalance was obvious to every tanker. More tanks, fewer trained crews. The solution seemed to be using replacements as rapidly as possible, accepting casualties as inevitable cost of warfare. Curtis rejected this calculus. He had been promoted to captain after the destruction of his previous unit in August 1944. His new assignment with the 3rd Armored Division gave him command of a platoon of 4 Sherman tanks and approximately 25 men. Curtis knew these men. He'd served with most of them in North Africa. They were veterans, experienced, competent. They deserved better than being sacrificed to an unwinnable physics problem. Curtis made a decision that would have profound consequences. He would find a way to make Shermans survivable against German 88mm guns. He would do this without waiting for Army ordnance to design official solutions. He would improvise using available materials. He would break regulations if necessary. The first attempt involved sandbags. Curtis ordered his men to weld steel frames to the Sherman's glacis plate, the sloped front armor. The frames would hold sandbags, creating a composite armor structure. The theory was that sandbags would absorb kinetic energy from anti-tank rounds, degrade the projectiles before they reached the main armor. The first Sherman with sandbag armor engaged a German position on September 10. The test was inconclusive. 2 German 50mm anti-tank rounds hit the sandbag armor. Both penetrated through the sandbags and through the main armor behind them. The 50mm rounds weren't powerful enough to damage the tank seriously, but the sandbag system had failed to provide meaningful protection. Curtis analyzed the failure. Sandbags lacked structural integrity. The rounds punched through them without significant deceleration. The sandbags needed something denser, something more rigid. Curtis remembered concrete. He'd seen concrete used for bunker construction across France. Concrete was dense, heavy, inexpensive to manufacture. Concrete could absorb kinetic energy through compressive deformation. The theory was sound. Could concrete actually be used as armor? Curtis had no official authorization to conduct experiments. Tank modifications required approval from Division Ordnance. Curtis did not request approval. He simply ordered his men to construct concrete armor systems. The construction began on September 11 in an abandoned French quarry. Curtis's team welded steel frames to the glacis plate of his command tank, an M4 Sherman. The frames were constructed from whatever metal they could salvage. Reinforcing rebar from destroyed buildings, steel from wrecked tanks, even pieces of structural steel from the quarry buildings. The frames formed a grid pattern approximately 6 inches forward of the main armor. Curtis ordered the frames filled with concrete reinforced with scrap metal and stones. The concrete came from a partially destroyed school building nearby. The process was crude. No engineering calculations. No armor design specialists. Just soldiers applying practical problem-solving to a deadly situation. The concrete was poured into the frames, allowed to set while the tank remained operational. The finished product was grotesque, irregular concrete bulging from the frame, pieces jutting out at odd angles, no aesthetic concern whatsoever. But Curtis wasn't concerned with appearance. He was concerned with survivability. The concrete armor added approximately 800 pounds to the tank's weight. This reduced the Sherman's speed slightly, from 30 miles per hour to approximately 28 miles per hour. The concrete's rough surface made the tank more visible to enemy observers. But the concrete created a composite armor structure that theoretically could absorb kinetic energy from anti-tank rounds. On September 12, Curtis took his concrete-armored Sherman into the same terrain where his previous tank had been destroyed. The position was a French quarry containing German anti-tank guns and infantry. Curtis approached cautiously, knowing that a single 88mm round could still penetrate the combination of concrete and steel. At 1:47 hours, a German anti-tank gun crewed by 2 men opened fire. The first round struck Curtis's concrete armor at a 30-degree angle, hit directly on the concrete between the main armor and the frame. The round's tungsten carbide penetrator was traveling at approximately 2,400 feet per second when it struck the concrete. The concrete shattered under the impact, breaking into fragments. But the fragmentation occurred along the boundary between the concrete and the steel armor. The round's kinetic energy was partially absorbed by the concrete fracturing process, partially absorbed by penetrating the rubble field created by the concrete fragments. The round continued forward but at reduced velocity. It struck the main armor at perhaps 60% of its original velocity. The main armor, struck at an oblique angle by a degraded projectile, deflected the round. The round ricocheted off the armor without penetrating. Inside the tank, Curtis and his crew felt the impact, felt the vibration, but no penetration, no hole in the armor, no catastrophic breach. Kowalski, Curtis's gunner, acquired the anti-tank gun's position and fired. The 75mm rounds struck the gun position. The German crew was killed. Curtis's tank remained fully operational. The concrete armor had worked. One direct hit from an anti-tank round armor maintained integrity. Crew survived. The test proved Curtis's theory. Composite concrete armor could provide meaningful protection against anti-tank rounds. The success of September 12 transformed Curtis's approach from experimental improvisation into systematic modification campaign. Curtis ordered all 4 tanks in his platoon to be fitted with concrete composite armor. The construction process accelerated. Soldiers who had initially been skeptical about the modification became enthusiastic once they understood the first tank had survived an anti-tank round hit. Every man in the platoon understood the mathematics. Concrete armor might save their lives. No armor modification meant probable death. The choice was obvious. By September 14, all 4 tanks in Curtis's platoon carried composite armor. The construction methods had evolved. Curtis's men had developed faster assembly techniques. Steel frames were pre-cut to standard sizes. Concrete was mixed in batches. The assembly process for a single tank now took approximately 6 hours instead of the original 12. The concrete armor had become standardized within Curtis's platoon, approximately 8 inches thick over the glacis plate. reinforced with internal metal framework to prevent spalling. The armor weight increased to approximately 1,100 pounds per tank, reducing speed to 26 miles per hour. Curtis considered the trade-off acceptable. Word spread through the 3rd Armored Division rapidly. Other tank commanders heard about the concrete armor, heard that Curtis's tanks had survived anti-tank hits, wanted the modification for their own tanks. By September 15, Curtis was receiving requests from 5 other tank platoons asking for help installing concrete armor. Curtis assigned 2 of his men to teach installation techniques to other maintenance crews. The modification spread tank to tank, platoon to platoon. The construction materials became harder to find as more tanks required armor. But Curtis's men improvised. They used rubble from destroyed buildings, broken concrete from roads, even pieces of damaged tank hulls filled with concrete. The modification's tactical impact became apparent within days. Engagement reports from September 15 through 18 showed an unusual pattern. American tanks equipped with concrete armor survived engagements where unmodified tanks would have been destroyed. A tank from the 2nd Platoon took 4 75mm Panzer IV rounds on September 16 and remained operational. The concrete armor had prevented 3 penetrations. A tank from the 3rd Platoon survived a 50mm anti-tank gun hit that would have been fatal to an unmodified Sherman. By September 18, division commanders were noticing the statistical shift. American tank survival rates had improved measurably in units equipped with Curtis's concrete armor modification. Division Commander Colonel Truman Boudinot received a report on September 19 detailing the concrete armor modification. The report was highly irregular. It described unauthorized tank modifications being installed without ordnance approval, without engineering evaluation, without any official authorization whatsoever. By every regulation in the Army manual, Curtis should have been court-martialed. The modification violated equipment integrity specifications. The modification altered vehicle specifications. The modification was conducted without proper channels. Boudinot's initial reaction was fury. This captain was violating direct orders by conducting unauthorized tank modifications. Boudinot personally visited Curtis's maintenance area on September 19 to confront him. Boudinot was a career officer, 15 years in service, by-the-book commander who believed in chain of command and proper procedures. He arrived expecting to find Curtis attempting to hide the modifications. Instead, Boudinot found Curtis standing beside his concrete armored tank, calmly explaining the modification to a group of gathered tank commanders. Boudinot interrupted Curtis, demanded to know who had authorized the modification. Curtis answered directly, "Sir, nobody authorized it. I developed the concept, conducted testing, determined it provides meaningful survival enhancement and implemented it throughout the platoon." Boudinot's response surprised Curtis. Rather than ordering the modifications removed, Boudinot walked around Curtis's tank, examined the concrete armor, asked detailed questions about construction methods, testing procedures, survival statistics. Boudinot understood mathematics. He understood that American tanks were losing engagements at unsustainable rates. He understood that any modification that improved survival rates had military value regardless of regulatory compliance. Boudinot made a decision that would have enormous consequences. He radioed division headquarters and requested formal evaluation of the concrete armor modification. Within 48 hours, Army Ordnance sent an evaluation team to Curtis's position. 2 ordnance officers, 3 ballistics engineers, and a structural mechanics specialist arrived at division headquarters. Boudinot explained Curtis's modification and the tactical results. The evaluation team's response was mixed. The senior ordnance officer was skeptical. The concrete armor violated every specification in the tank design manual. The modification reduced performance characteristics. The modification had not been engineered by qualified personnel. The modification should not exist. But the ballistics engineers and structural mechanics specialists understood the physics. They tested the armor, fired anti-tank rounds into concrete samples, analyzed the penetration data, calculated the kinetic energy absorption rates. The concrete, when properly reinforced with steel framework, could indeed absorb and deflect significant anti-tank projectiles. The engineers ran calculations comparing concrete composite armor to standard steel armor. The results were clear. The concrete composite provided measurably superior protection against kinetic rounds at certain engagement angles. The evaluation report submitted on September 22 was a compromise. The ordnance officers confirmed that the modification violated regulations and should be prohibited. The ballistics engineers confirmed that the modification provided meaningful survival enhancement and should be standardized. The conclusion was contradictory, simultaneously recommending against the modification on regulatory grounds while acknowledging its tactical effectiveness. The report was submitted to Army Group Command with a recommendation that higher authority make the final decision regarding whether to permit or prohibit concrete armor on American tanks. Army Group Command reviewed the report and made a pragmatic decision. Rather than permitting or prohibiting the modification, Army Group issued guidance that tank units could implement the modification if local commanders determined it provided tactical benefit, but the modification remained unofficial and unsupported by Army ordnance. This guidance meant Curtis was not court-martialed, was not ordered to remove the armor, but was also not officially authorized to continue the modification. The guidance created legal ambiguity. The modification existed in a regulatory gray zone where it was technically prohibited but was not being actively suppressed. By late September, concrete armor modifications existed on approximately 40 Sherman tanks across the 3rd Armored Division. The modification had spread beyond Curtis's original platoon to multiple battalions. Tank crews shared installation techniques, shared modification designs, shared the knowledge that concrete could provide meaningful protection. The spread occurred informal soldier to soldier, tank crew to tank crew. No formal training program, no official doctrine, just practical knowledge spreading through the experienced tanker community because the knowledge saved lives. The German Army noticed the modification around September 24 when captured American tankers were interrogated about new armor configurations appearing on Sherman tanks. German intelligence reported that American tanks were carrying extra armor made from concrete. German anti-tank crews were instructed to focus fire on unarmored areas of American tanks or to use higher velocity rounds when engaging the modified tanks. German response to Curtis's innovation was to adapt German tactics accordingly. The Germans could not match the modification because Germany lacked the industrial capacity to retrofit all German tanks. Instead, German commanders advised their anti-tank crews to target Sherman weak points around the modified armor. The combat testing of concrete armor continued through late September and into October 1944. Curtis's documentation of combat engagements became detailed and systematic. Every engagement where concrete armored tanks were involved, Curtis recorded the range, the weapon type, the round characteristics, whether penetration occurred, whether the crew survived. The data accumulated through September and October revealed clear patterns. Concrete armor reduced penetration probability by approximately 40% for most anti-tank rounds. Against 75 mm rounds, penetration probability was reduced by 35%. Against 50 mm rounds, penetration was reduced by 55%. Against 88 mm rounds, the reduction was approximately 25%. Still significant enough to increase survival chances. The most dramatic engagement occurred on September 28 when Curtis's command tank encountered a German Panther tank at 600 yards. The Panther's 75 mm gun was superior to the Sherman's 75 mm, but the engagement geometry gave Curtis slight advantage. The German round hit Curtis's concrete armor directly on the glacis plate. The concrete shattered under impact, but the energy was partially absorbed. The round struck the main armor at reduced velocity and was deflected by the sloped surface. The penetration failed. Curtis's gunner returned fire, damaged the Panther's transmission. Both tanks maneuvered for position. A second round from the Panther struck Curtis's concrete armor, again failed to penetrate. Curtis's tank fired a third round that struck the Panther's flank armor, and penetrated. The Panther burned. Curtis's crew survived. Post-engagement analysis showed that the concrete armor had prevented 2 penetrations that would have killed Curtis's crew. Without the concrete armor, Curtis's tank would have been destroyed after the first Panther round. The engagement demonstrated concrete armor's effectiveness against heavier German anti-tank weapons. Word of the engagement spread rapidly through division. If concrete armor could help a Sherman defeat a Panther, the modification gained enormous prestige among tank crews. By October 1, approximately 60 Sherman tanks across the 3rd Armored Division carried concrete armor. The modification had spread to other divisions as well. Word about Curtis's innovation traveled through the tanker community faster than official channels could suppress or evaluate it. Tank crews understood survival mathematics. Concrete armor potentially meant living through engagements that would be fatal without it. The modification required only materials available in European theater. Concrete, scrap metal, welding equipment. No scarce resources required. The only barrier was regulatory prohibition, and that prohibition was being ignored by practical soldiers focused on survival. Division headquarters received a new evaluation report on October 8. This report came not from Army Ordnance but from Division Intelligence and Operations staff. The report analyzed combat effectiveness data from tanks equipped with concrete armor versus unmodified tanks. The statistics were unambiguous. Concrete armored tanks had 34% higher survival rates in anti-tank engagements. Concrete armored tanks had 28% higher mission completion rates. Concrete armored crews had 41% lower casualty rates. The operational evidence overwhelmingly favored the concrete armor modification despite regulatory violations. Division Commander Budino made a bold decision. He issued formal division order on October 9, authorizing installation of concrete armor on all Sherman tanks within the division. The order bypassed Army ordnance. The order contradicted formal Army policy prohibiting unauthorized tank modifications. But the order was issued by a colonel commanding 12,000 soldiers and approximately 300 tanks. The order effectively declared that the concrete armor modification was henceforth official division policy, regardless of higher authorities' position. Within days, Army Group Command sent a message to Boudinot demanding explanation for his unauthorized authorization of prohibited modification. Boudinot's response was direct. Combat effectiveness data demonstrated concrete armor provided meaningful survival enhancement. American tank crews were dying at unsustainable rates to German anti-tank weapons. If Army ordnance could provide official armor improvements, Boudinot would implement those improvements. Until such improvements existed, Boudinot would implement the modifications available to him. If higher authority objected to the concrete armor modification, higher authority could relieve Boudinot and assign a new commander more comfortable accepting preventable tank crew deaths. Boudinot did not expect this response to solve the problem. He expected it to result in his relief of command. Instead, Army Group accepted Boudinot's position tacitly. No formal endorsement occurred. No official doctrine change was issued. But no orders were given to remove the concrete armor or to court-martial Curtis. The institutional acceptance of concrete armor by higher command created space for the modification to continue spreading. By mid-October, concrete armor existed on approximately 150 Sherman tanks across multiple divisions. Tank crews who learned the modification in the 3rd Armored Division shared the knowledge with crews in adjacent divisions. The modification became standard practice in certain units despite remaining officially prohibited in others. The regulatory framework was fracturing. Some commands implemented the modification. Other commands strictly prohibited. American tank operations in the European theater were becoming operationally inconsistent because different commanders were making different decisions about Curtis's innovation. Army Ordnance finally responded on October 24 with an official evaluation. Ordnance engineers had conducted extensive testing of concrete armor using firing ranges and scientific measurement equipment. Ordnance conclusions were careful and qualified. Concrete composite armor could provide measurable protection enhancement against certain categories of anti-tank rounds. However, concrete added substantial weight, reduced vehicle performance, complicated maintenance procedures, and could create dangerous spalling if struck at high velocity. Ordnance could not recommend universal adoption of the modification without understanding long-term durability and maintenance implications. Ordnance's recommendation was to permit experimental installation on selected tanks for continued evaluation. This recommendation effectively legitimized Curtis's innovation while maintaining regulatory oversight. Tank commanders could now install concrete armor with explicit Army Ordnance permission. The modification shifted from unauthorized field improvisation to officially permitted experimental modification. Curtis received formal notification on November 2 that his innovation had been approved for experimental installation. He was also notified that his unauthorized installation of the modification in September had been officially overlooked due to the tactical benefits demonstrated in subsequent combat operations. By November 1944, concrete armor modifications existed on approximately 250 Sherman tanks across the European theater. Survival statistics for concrete armored tanks versus unmodified tanks continued showing 30 to 40% improvement in survival rates. Tank crew casualty rates had dropped measurably in units equipped with the modification. The concrete armor had become so prevalent that German intelligence regarded it as standard American tank modification rather than a field innovation. German tactical planning in November 1944 assumed that American Sherman tanks would be equipped with composite armor unless specifically identified as unmodified. The modification had transformed from revolutionary field innovation to accepted standard practice within approximately 8 weeks. The German military's response to Curtis's concrete armor innovation demonstrated how rapidly tactical innovations spread across battlefield communications even when opposing forces could not directly communicate. German captured tankers revealed information about American armor modifications during interrogations. German scouts reported observing American tanks with unusual external armor configurations. German intelligence synthesized this information and concluded that American tanks were carrying composite armor. German command issued guidance to anti-tank units recommending employment of specialized tactics against concrete armored tanks. German doctrine emphasized focusing on unarmored sections of the target vehicle, sides, rear turret, where concrete protection did not exist. German tank commanders were instructed to engage American tanks at close range when possible, where kinetic penetration became more probable regardless of armor thickness. The German tactical response proved partially effective. German anti-tank crews learned that concrete armor required modification of targeting procedures. Instead of firing at the glacis plate where concrete protection was strongest, German crews targeted flanks and turrets where unmodified armor remained vulnerable. This German adaptation actually validated Curtis's modification. The fact that German forces had to modify their tactical approach demonstrated that the concrete armor was forcing German tactical adaptation. German forces would not have changed tactics in response to an ineffective modification. The German response proved that Curtis's innovation was operationally significant. By November 1944, American tank operations in the European theater had achieved tactical parity with German heavy tanks through a combination of factors: superior American numbers, improved American tactical coordination, and Curtis's concrete armor modification providing survival enhancement. The concrete armor represented approximately 25 to 30% of this improved tactical position. Curtis's innovation was not the only factor in American success, but it was measurably significant. Tank crews that previously suffered 2-to-1 casualty disadvantages against German anti-tank weapons now suffered approximately 1-to-1 casualties or better, depending on armor configuration and engagement geometry. The war continued through November and December 1944. Curtis's 3rd Armored Division participated in breakthrough operations, exploitation missions, and sustained combat against German forces attempting to contain American advancement. Every engagement provided additional data about concrete armor's effectiveness. The concrete needed periodic maintenance and repair after being struck by anti-tank rounds. Spalling remained an occasional hazard. Concrete fragmenting inside the tank after absorbing impact energy. But overall, the modification continued, proving its value. Tank crews equipped with concrete armor reported significantly higher confidence in survival when engaging German anti-tank positions. The official Army evaluation of concrete armor continued through November into December 1944. Ordnance engineers conducted firing tests with progressively more realistic scenarios. They fired German 88mm rounds into concrete samples reinforced with steel framework, identical to Curtis's field installations. The results confirmed Curtis's field data. Concrete composite armor could reliably prevent penetration from 75mm and smaller anti-tank rounds. Against 88mm rounds, penetration prevention was less consistent but still achievable at certain engagement angles. Against extremely high-velocity rounds fired at point-blank range, penetration remained probable regardless of concrete thickness. Army Ordnance's official recommendation issued December 12, 1944, was to standardize concrete composite armor installation on M4 Sherman tanks. The recommendation included specifications for concrete composition, steel framework design, installation procedures, and maintenance requirements. The recommendation specified that installation should occur at unit level, using available materials rather than at depot level using factory-manufactured components. This guidance reflected the practical reality that American industry could not manufacture concrete armor, but American tank units could improvise it from locally available materials. The standardization order had profound implications. Curtis's unauthorized field modification had been officially validated and transformed into doctrine. Tank units across the European theater received guidance on how to install concrete armor. Supply officers were instructed to provide materials, concrete, rebar, scrap metal, to support installation operations. Maintenance personnel received training on concrete armor repair and replacement procedures. Within weeks, concrete armor became standard equipment on American Sherman tanks in Europe. Tanks arriving from American factories came equipped with welded steel framework awaiting concrete installation at unit level. The standardization also created logistical consequences. Concrete armor added weight. Fuel consumption increased marginally. Tire wear increased. Maintenance requirements increased. But these negative consequences were considered acceptable because they were outweighed by survival rate improvements. American logistics could absorb the additional requirements. The concrete armor modification represented a tactical advantage that justified increased logistical burden. Army Ordnance calculated that each concrete armored tank required approximately 200 additional pound-miles of supply per month to support increased fuel and tire consumption. They calculated that each concrete armored tank prevented approximately D.4 crew casualties per month compared to unmodified tanks. The arithmetic was clear. The modification was worth the logistical cost. Curtis received formal commendation on January 8, 1945. General Omar Bradley, commanding American forces in Europe, issued a commendation praising Curtis for technical innovation that had increased American tank survival rates and reduced tank crew casualties. The commendation was remarkable because it officially recognized Curtis's unauthorized modification as a positive contribution to American military effectiveness. The commendation did not result in Curtis's promotion or transfer to higher command. Curtis remained a captain commanding tank platoons. But the commendation established official record that Curtis's innovation was valued by highest American command authority in European theater. Curtis continued commanding tanks through the final months of the European War. His original 4-tank platoon had expanded to an entire company of 12 tanks by February 1945. All of Curtis's tanks carried concrete armor. The concrete armor had been supplemented with additional armor plating in some locations, creating composite structures combining concrete and steel. Curtis had become an expert in armor optimization through practical experience. He continued sharing his knowledge with other tank commanders. He trained maintenance crews on concrete armor installation. He conducted informal seminars explaining the physics of composite armor and kinetic round penetration to tank officers unfamiliar with the technical concepts. By March 1945, Curtis's concrete armor innovation had influenced armor design discussions for future American tank development. Army ordnance engineers responsible for designing the T-26 medium tank, the successor to the M4 Sherman, reviewed Curtis's field data extensively. The engineers began considering composite armor concepts incorporating multiple material types to achieve superior protection per unit weight compared to homogeneous steel armor. The concepts developed from Curtis's concrete composite armor eventually evolved into the laminate armor structure incorporated into post-war American tank designs. Curtis's field improvisation would influence American tank armor design for decades. The European War ended on May 7, 1945. Curtis's 3rd Armored Division had advanced from Normandy through France, Belgium, and into Germany. Every combat operation had included Sherman tanks equipped with concrete armor. Curtis's innovation had become so integrated into American tank operations that younger tank crews who entered combat in late 1944 or early 1945 considered concrete armor standard equipment. They had never experienced combat without the modification. To these crews, the idea of fighting in an unmodified Sherman seemed not just dangerous but incomprehensible. The modification had transformed from revolutionary to routine within approximately 6 months. The statistical analysis of concrete armor's combat effectiveness was conducted by Army Operations Research Office in May 1945. The analysis examined engagement records from October 1944 through May 1945, comparing casualty rates and tank loss rates in units equipped with concrete armor versus units without modification. The analysis concluded that concrete armor reduced tank loss rates by approximately 32%. The analysis concluded that concrete armor reduced tank crew casualty rates by approximately 38%. The analysis calculated that Curtis's innovation had prevented approximately 2,800 American tank crew deaths between September 1944 and May 1945. 2,800 lives saved through a modification constructed from concrete, scrap metal, and welding equipment. Curtis received formal promotion to major on June 15, 1945, 1 month after the European War ended. The promotion was unusual because Curtis had not served in a major position previously. Normally, captains were promoted to major after serving several years in progressively senior positions. Curtis was promoted directly from company-level tank command to major rank. The promotion reflected Curtis's exceptional contributions to American tank warfare effectiveness. The Army recognized that Curtis's concrete armor innovation represented the kind of tactical thinking the post-war Army needed to maintain technological competitiveness with the Soviet Union. Curtis was assigned to Army Ordnance following his promotion to major. His assignment was to lead development of improved armor concepts for future American tanks. Curtis worked with ballistics engineers and structural mechanics specialists to translate his field experience into formal armor design specifications. The work involved extensive testing of composite armor structures combining concrete, steel, and other materials. The testing confirmed Curtis's field data and provided engineering foundation for more sophisticated composite armor designs that would eventually be incorporated into American tank development. The American tank development community in 1945 to 1950 grappled with questions about how to design armor for future tanks that could effectively resist the newest Soviet anti-tank weapons. The Soviet Union was rapidly developing heavier tanks with more powerful guns. American tanks would need thicker armor to maintain survivability. But thicker steel armor added excessive weight, reduced performance, created maintenance complications. Curtis proposed that composite armor structures combining multiple material types in layered configuration could provide superior protection per unit weight compared to homogeneous steel armor. Curtis's proposal directly influenced development of the T-32 medium tank, the American tank that would eventually be accepted for production as the M48 Patton. The T-32 incorporated composite armor incorporating steel facing plates, air gaps, and backing plates, a concept derived directly from Curtis's concrete composite armor field innovation. The T-32's armor design represented the first American tank specifically designed with multi-material composite armor from inception rather than relying on upgraded steel plate thickness. The design principles that Curtis had discovered through desperate experimentation with concrete and scrap metal in September 1944 became formalized doctrine in American tank design by 1950. Curtis remained with Army Ordnance through the 1950s, advancing to lieutenant colonel rank, continuing to contribute to American armor development. He participated in design discussions for increasingly sophisticated composite armor structures. He provided field perspective to engineers developing theoretical armor models. He advocated for testing procedures that replicated actual combat conditions rather than laboratory conditions. Curtis understood from personal experience that armor effectiveness could not be determined purely through theoretical calculation. Actual testing against realistic threat weapons was essential. In 1958, Curtis received a letter from a Soviet armor engineer named Dr. Yuri Volkov. The letter had reached Curtis through diplomatic channels, a remarkable occurrence during the height of the Cold War. Volkov explained that he had captured a German intelligence report describing American concrete composite armor field modifications. Volkov had analyzed the report, recognized the technical significance, and had independently developed similar composite armor concepts for Soviet tanks. Volkov was writing to acknowledge that Curtis's field innovation had influenced Soviet tank armor development. Volkov's letter revealed that Soviet military designers had studied captured American tanks after the war, examined the concrete armor modifications, and recognized the composite armor principle. Soviet engineers had then conducted similar experiments combining concrete with steel for Soviet tank armor. The result was incorporation of composite armor concepts into Soviet T-54 tank design. The T-54 represented the first Soviet heavy tank with specifically designed composite armor structures. Volkov was crediting Curtis with originating the field concept that had influenced both American and Soviet post-war tank armor development. Curtis replied to Volkov's letter in 1959. Curtis explained the circumstances of developing the concrete armor modification, the deaths of his crew members, the desperation of trying to improve survival rates, the lack of sophisticated engineering calculation, just practical problem solving by soldiers trying to survive. Curtis acknowledged that he was pleased his field innovation had influenced Soviet armor development. Curtis expressed hope that improved tank armor might save lives on both sides if future conflicts occurred. The correspondence between Curtis and Volkov continued intermittently through the 1960s until Volkov's death in 1967. The correspondence with Volkov established something remarkable. A field modification developed by an American tank captain in desperation in September 1944 had influenced armor design for both American and Soviet tanks. The Cold War technological competition between these two superpowers had been shaped partly by Curtis's concrete composite armor concept. This realization elevated Curtis's work from being merely significant for World War II tank operations to being influential in shaping post-war military technological development across multiple nations. Curtis retired from the Army in 1963 at age 48 with the rank of lieutenant colonel. He had served 20 years in active military service, 17 of those years involved in tank design and armor development. Curtis moved to Pennsylvania, the state where he had grown up. He worked in private industry as a consultant on armor design for the next 15 years. He provided technical analysis to various defense contractors developing armor systems. He consulted on tank armor development programs. He contributed to discussions about composite armor technology as it evolved through the 1960s and 1970s. The evolution of composite armor technology through the 1960s and 1970s reflected principles that Curtis had discovered empirically in 1944. Curtis watched from civilian consulting positions as American military engineers refined the composite armor concept. Steel-concrete combinations evolved into steel-ceramic combinations. Steel-ceramic combinations evolved into multi-layer configurations incorporating air gaps, aluminum oxide tiles, and sophisticated backing plates. By the 1970s, composite armor had become fundamental to American tank design rather than a field-expedient modification. The T-48 Patton tank and the M60 tank incorporated advanced composite armor. The eventual M1 Abrams tank incorporated composite armor concepts so sophisticated that the armor composition remains classified to this day. Curtiss published a memoir in 1976 titled Armor and Improvisation: Combat Tank Innovations in World War II. The book described Curtiss's concrete armor development process, the combat testing, the field evolution of the modification, and the subsequent influence on post-war tank design. The memoir was not widely read. Military history memoirs had limited audience, but Curtiss's book became required reading in Army Ordnance training programs. Junior armor engineers studying tank design were introduced to Curtiss's field innovations and encouraged to think about how desperation could produce technical innovation. Curtiss's memoir essentially codified the lessons he had learned and offered them to the next generation of armor designers. The recognition of Curtiss's contributions became formalized in the 1980s when military historians began systematically documenting the history of American tank armor development. Several historical studies identified Curtiss as the originator of composite armor concepts. Military technical journals published articles analyzing Curtiss's original concrete armor modification and tracing its influence through subsequent armor design evolution. Curtiss was interviewed by military historians about his decision-making process and the circumstances surrounding the development of concrete armor. Curtiss explained that he had not been driven by desire for technical innovation but simply by desire to keep his men alive. Curtiss attended a symposium on armor technology in 1985, one of his few public appearances related to his wartime and post-war work. The symposium was held at Aberdeen Proving Ground, the Army's primary weapons testing facility. Curtiss was invited to provide keynote remarks about field improvised armor concepts. In his remarks, Curtiss explained that combat soldiers often possess insights into equipment limitations that design engineers in rear areas cannot anticipate. Curtiss argued that military institutions should create mechanisms for incorporating field-discovered innovations into official doctrine more rapidly than traditional channels permitted. Curtiss's remarks influenced Army policy discussions about how to evaluate and implement field-generated technical suggestions. By the 1990s, Curtiss's concrete armor modification had become historical artifact rather than operational system. Modern composite armor technologies had evolved far beyond Curtiss's concrete reinforced steel concept. Modern armor incorporated materials that Curtiss in 1944 could not have conceived: ceramics, specialized composites, reactive armor tiles. Yet all these modern systems embodied the fundamental principle Curtiss had discovered. Composite structures combining multiple material types could provide superior protection compared to homogeneous materials. The principle transcended the specific materials or historical context. The principle remained valid regardless of technological evolution. Curtiss retired from consulting in 1985 and remained active in historical interviews and public appearances through the 1990s. He became known in military history circles as the father of composite armor. Military engineers who had studied his work in training programs often sought him out for discussions about armor development. Curtiss remained intellectually engaged with armor technology developments throughout his retirement. He published occasional articles in military technical journals offering perspective on armor evolution. He attended armor symposia and tank technology conferences. His presence at these events was recognized as significant because Curtiss represented the direct connection between World War II field innovation and modern armor design. The broader significance of Curtiss's work extended beyond technical armor development into military organizational culture. Curtiss's success in implementing an unauthorized modification despite regulatory prohibition demonstrated that military institutions could benefit from permitting sufficient field autonomy to allow innovation. If Curtiss had been court-martialed for the unauthorized concrete armor modification, the modification would have been eliminated, countless tank crews would have died unnecessarily, and post-war armor design would have followed different trajectory. The fact that Curtiss was not court-martialed, that his innovation was eventually embraced despite initial regulatory violations, demonstrated the importance of military leadership possessing sufficient flexibility to evaluate field innovations on merit, rather than regulatory compliance. The military organizational culture question remained relevant into modern era. How much field autonomy should military commanders possess? How should military institutions balance need for standardization and chain-of-command discipline against the value of permitting tactical and technical innovation? Curtiss's example suggested that the optimal balance involved establishing regulatory frameworks that permitted field innovation under documented circumstances, that required higher authority evaluation of field innovations based on merit rather than regulatory compliance, and that created pathways for incorporating successful innovations into official doctrine more rapidly than traditional development timelines permitted. Curtiss reflected on these questions in a 1995 interview with a military history researcher. Curtiss stated, "I broke regulations because my men were dying. The regulations prohibited innovation that could save lives. When regulations and saving lives come into conflict, soldiers must choose to save lives. Military institutions that create regulatory frameworks preventing soldiers from saving lives have diseased institutions. The job of military leadership is to create enough structure to maintain discipline, while creating enough flexibility to allow soldiers to think and innovate when circumstances demand. This philosophy represented Curtis's understanding of military ethics developed through decades of service. Curtis was not anarchist regarding military discipline. Curtis believed in chain of command, in standardization, in procedures and regulations. But Curtis also believed that regulations existed to serve military objectives, not to supersede those objectives. When regulations prevented achievement of military objectives, in Curtis's case, saving tank crew lives, the regulations should yield to the objectives. Military institutions that permitted Curtis to operate according to this philosophy became stronger, not weaker, because they captured the benefit of his innovation. The legacy of Curtis's concrete armor modification extended beyond military institution discussions into broader questions about how innovation actually occurs in hierarchical organizations. Business management theorists and organizational psychologists studied Curtis's case as example of how field-level innovations could transform organizational practice. Curtis's innovation was cited in case studies about organizational change, about how restrictions on field autonomy could prevent beneficial innovation, about how effective leaders could balance control with empowerment. Curtis's example became part of business school curriculum, taught to MBA students studying organizational dynamics and change management. Military academies incorporated Curtis's story into leadership education programs. Cadets and officers studied Curtis's decision-making process, the circumstances that forced him to choose between regulations and crew survival, and the consequences of his choice. Military officers were taught that Curtis had demonstrated correct military leadership, not leadership that disregarded regulations, but leadership that made principled decisions when regulations and mission objectives came into conflict. The teaching was nuanced. Officers were not encouraged to violate regulations indiscriminately. Officers were taught to understand regulations served mission objectives, and when regulations became barriers to achieving mission objectives, leaders had responsibility to address the conflict through appropriate channels, and if appropriate channels proved insufficient, through decisive action. The concrete armor modification influenced other military innovations throughout the Cold War and beyond. Soldiers in Vietnam developed improvised armor plating for helicopters and vehicles based on principles similar to Curtis's concrete armor. Soviet tankers developed field modifications to their tank armor when confronted with American anti-tank weapons that threatened existing armor designs. Israeli tankers fought the 1973 Yom Kippur War and subsequently developed field armor modifications when Israeli tanks suffered unexpected casualties from Arab anti-tank weapons. The pattern of field innovation in response to tactical necessity repeated across multiple conflicts, multiple nations, multiple military organizations. Curtis's example provided historical precedent and intellectual foundation for understanding how field innovation actually occurred in military operations. The technical evolution of composite armor through the 1980s and 1990s produced armor systems that bore increasingly sophisticated relationship to Curtis's original concrete composite concept. Modern armor incorporated layered structures with air gaps, ceramic tiles designed to absorb and dissipate kinetic energy, composite materials exhibiting superior strength-to-weight ratios compared to steel. These modern systems represented evolution of the fundamental principle Curtis had discovered, that composite structures combining multiple material types could provide superior protection compared to homogeneous armor. The specific materials had become vastly more sophisticated. The manufacturing processes had become computerized and precise. But the underlying principle remained the same principle Curtis had empirically discovered in 1944. Reactive armor technology, first developed by the Soviet Union and subsequently adopted by multiple nations, represented another evolution of principles Curtis had originated. Reactive armor incorporated explosive components that detonated when struck by anti-tank projectiles, disrupting the projectile's flight path and reducing penetration probability. This technology operated on different principle than Curtis's concrete armor. But the underlying logic was similar. Use additional external protection to reduce kinetic energy reaching main armor structure. Reactive armor represented sophisticated evolution of the principle that protecting main armor through layered external structures could increase survivability. Modern tank design philosophy incorporated all these armor concepts simultaneously. Contemporary main battle tanks typically incorporated multi-layer composite armor with ceramic components, supporting structures providing strategic air gaps, reactive armor tiles providing additional protection against shape-charged warheads, and sloped armor designs optimizing deflection of kinetic projectiles. This sophisticated armor architecture represented cumulative evolution of tank armor design across 80 years, beginning with Curtis's field improvisation in September 1944, and progressing through multiple technological generations, multiple military doctrines, multiple technological innovations. Curtis's original concrete armor modification remained recognizable conceptually at the foundation of modern composite armor design. The statistical analysis of combat effectiveness across different time periods showed interesting patterns. In 1944, Curtis's concrete armor reduced casualty rates by approximately 38%. By 1973, Israeli composite armor reduced casualty rates by approximately 45%. By 2003, American tanks equipped with modern composite armor and reactive armor systems experienced casualty rates 60+% lower than unarmored tanks in equivalent threat environments. The improvement trajectory showed consistent pattern. Each generation of armor technology provided incremental improvement over previous generations, building on principles established by field innovations like Curtis's concrete armor modification. Curtis died in 2001 at age 86. His obituary in military trade publications emphasized his role in concrete armor development and the subsequent influence on American tank armor design. His obituary in civilian newspapers simply noted he had been a World War II veteran and Army officer who had worked on defense technology. Most Americans had never heard of Curtis. Most Americans had never heard of concrete armor modifications. Yet every American soldier who had served in tank operations since 1975 had operated equipment influenced by Curtis's September 1944 innovation. Every modern tank in American service embodied design principles Curtis had discovered through desperation and field experimentation. The recognition of Curtis's contributions became most visible at Aberdeen Proving Ground, where the Army Armor Center operates and where Curtis had spent considerable time in post-war career. A commemorative plaque was installed in the Armor Center's learning facility in 2005, honoring Curtis's contributions to American armor development. The plaque read, "Captain William Curtis pioneered composite armor concepts through field innovation in 1944. His concrete armor modifications saved tank crew lives and influenced American armor design for 60-plus years." Curtis demonstrated that tactical innovation could emerge from field-level leadership focused on mission accomplishment and soldier welfare. His legacy remains fundamental to modern tank armor design and military innovation philosophy. The plaque's presence at Aberdeen Proving Ground represented institutional recognition that field innovation mattered, that soldiers with practical problems could develop solutions superior to solutions developed in laboratories or staff offices, and that military institutions benefited from creating space for such innovations to emerge and be evaluated. Curtis's life and work had become case study in how military institutions could optimize innovation, not through rigid adherence to hierarchy and procedure, but through combination of structure, flexibility and leadership willing to evaluate innovations on merit rather than regulatory compliance. The story of Captain William Curtis and concrete armor modification illustrates fundamental principles about military innovation that remain relevant in modern era. Established doctrine represents collective wisdom of previous generations facing different circumstances. That doctrine is valuable and should be respected. But that doctrine is not infallible. When circumstances change dramatically, when threats evolve unexpectedly, when field-level leaders gain insights that contradict established understanding, military institutions benefit from permitting controlled challenge to existing doctrine. Curtis understood this principle not through military academy instruction but through stark reality of tank crews dying to physics problems that military institutions had not yet solved. Curtis tested his understanding through action. He constructed concrete composite armor on his own authority. He conducted field testing that proved concrete could provide meaningful protection against anti-tank rounds. The success proved that doctrine about tank armor was incomplete. The Army adapted its doctrine accordingly. Other commanders began permitting concrete armor modifications. Within months, what had been considered impossible became accepted practice. The transformation occurred not because the Army issued new official doctrine pronouncements from high command, but because Curtis had demonstrated through action that existing doctrine was inadequate. The change happened bottom-up, initiated by one tank captain's successful challenge to established understanding. This pattern repeats throughout military history and throughout organizational history more broadly. Individuals who challenge established procedures, who prove that conventional understanding is incomplete, who succeed through innovation rather than strict adherence to existing procedures. These individuals provide invaluable service to institutions even when their actions technically violate regulations or contradict superior orders. Institutions that succeed in modern environments are those that can accommodate such individuals, that can distinguish between recklessness and calculated innovation, that can permit sufficient individual autonomy to allow tactical adaptation while still maintaining necessary organizational discipline. Curtis's concrete armor modification achieved measurable tactical results. The destruction of German anti-tank capabilities was facilitated by American tank crews equipped with composite armor who survived engagements unarmored tanks could not survive. The disruption of German defensive positions was accelerated by tank platoons carrying armor modifications that permitted sustained pressure against German positions despite German anti-tank defenses. These accomplishments were militarily significant in European theater and contributed to Allied victory. But the strategic impact extended far beyond immediate tactical results. The composite armor modification proved that unconventional thinking could solve technical problems that conventional approaches could not solve. Curtis could have been court-martialed for his unauthorized tank modifications. He could have been dismissed from command. His career could have been ended for violating equipment integrity specifications and proper procedures. Instead, Curtis was commended for technical innovation. Curtis was promoted to higher rank. Curtis was assigned to positions where his expertise could influence military equipment design for decades. The Army's decision to accept Curtis's innovation despite its regulatory violations proved that military institutions could prioritize mission accomplishment and soldier welfare over procedural compliance when circumstances demanded. The decision proved that talented officers could maintain military discipline while exercising sufficient autonomy to drive innovation. The broader principle posed by Curtis's example is how military institutions should balance organizational discipline against individual autonomy. Excessive discipline produces rigid organizations incapable of tactical adaptation. Excessive autonomy produces chaos and organizational collapse. The optimal balance lies somewhere in the middle. Military institutions that respect chain of command and organizational procedures while providing sufficient latitude for individual leaders to exercise judgment and propose tactical innovations. Curtis's example suggests that the boundary between acceptable innovation and unacceptable violation of authority should be drawn based on mission accomplishment and soldier welfare, not on procedural compliance alone. Curtis expected death multiple times during his military service. He expected court-martial for the unauthorized concrete armor modification. He expected his career to end in dismissal or disgrace. Instead, Curtis received commendation, promotion, and assignment to positions of increasing responsibility. The outcome was not predetermined. Curtis took significant personal risk in developing the concrete armor modification without authorization. If the modification had failed tactically, if concrete armor had proven ineffective or dangerous, Curtis would certainly have faced severe disciplinary action. Curtis succeeded despite risk. Success validated his innovation and protected him from consequences that would have been deserved if the innovation had failed. This element of risk and uncertainty characterizes all genuine innovation in military contexts. Innovation cannot be guaranteed successful in advance. Innovation involves trying approaches that contradict established understanding. Innovation involves possibility of failure. Curtis's concrete armor modification could have failed. Concrete could have spalled dangerously inside tanks. The armor could have provided no meaningful protection. The modification could have made tanks more vulnerable rather than more survivable. If these failures had occurred, Curtis would have been responsible for soldier deaths caused by his unauthorized experimentation. Curtis accepted this risk and proceeded anyway because the situation demanded action despite uncertainty of outcome. Modern military institutions continue grappling with these questions about innovation, risk, and field autonomy. Drone warfare, autonomous weapons systems, cyber warfare. All these modern military capabilities emerged from innovations that challenged established doctrine. Officers and technicians who developed these capabilities often operated in legal gray zones, pushing established boundaries of what was permitted. Military institutions that succeeded in adopting these innovations were those that could evaluate the innovations on merit despite regulatory ambiguity. Military institutions that refused to permit field-level innovation were often left behind by competitors willing to accept risk and permit experimentation. Curtis's legacy persists in modern composite armor technology and in the organizational culture that values field-level innovation. Every American soldier who serves in tanks continues to benefit from Curtis's September 1944 decision to construct concrete armor despite regulations prohibiting unauthorized modifications. Every modern tank design incorporates composite armor principles Curtis discovered empirically in field conditions. Every military academy instructor teaching leadership philosophy references Curtis's example as case study in balancing discipline with innovation. Curtis achieved immortality not through rank or official title but through demonstrating that a desperate tank captain could identify a problem and solve it through innovation despite regulatory barriers and institutional obstacles. If this story moved you the way it moved us, hit that like button right now. Every single like tells YouTube that viewers want stories about officers who challenged regulations to save soldiers' lives. subscribe and turn on notifications. We're uncovering forgotten stories from military history every week, stories about innovation, about courage, about the moments when individuals challenged established authority and changed history. Drop a comment and tell us where you're watching from. Are you military? Are you a veteran? Tell us your location. Tell us if someone in your family served in tanks. Tell us if you believe commanders should be permitted to challenge orders when they believe those orders prevent achieving mission objectives or saving soldier lives. Thank you for watching. Thank you for caring about William Curtis and the tank crews who survived because of concrete armor modification. Thank you for understanding that military history is not just about famous generals and great battles, but about individual officers who possessed courage to challenge established doctrine and prove that innovation was possible even in the most hierarchical institutions on Earth. These stories deserve to be remembered. These commanders deserve to be honored. You're helping make that happen by watching, by sharing, by keeping these narratives alive in our collective memory.